We're switching into chapter 2, where we're going to talk about the average rates of change and instantaneous rates of change. So the averages between 2 points and instantaneous in an instant at one particular point in time. We're going to analyze each one of these notions analytically, so through the formulas, numerically by using the actual data, and graphically by looking at some graphs. Because the graphical method is the most intuitive one, let's start there. So here's the graph of the COVID-19 vaccinations in Canada. The light green represents the number of people that have gotten at least one dose at any given period of time since the doses started first being offered. And the dark green graph corresponds to the number of people that were fully vaccinated. We're going to work with the at least one dose data for this example here. So here we're asked to find the average rate of vaccinations over the first 3 months of availability. So the first point here corresponds to December 14th, which means that in 3 months, we're looking at March 14th as our second point. So the question is, what is the average rate of vaccinations that occurred between these 2 points? Because we deal with averages all the time in real life, it might be easier before we jump into the formula to start thinking about the units. The average rates, as reported, were things like the number of vaccines per month or per day or per something, where per always, of course, represents division. So in general, averages is the number of new cases divided by the amount of time that spanned in between the 2 data points being collected. So in our case here, the average rate of vaccination is equal to the number of new vaccinations. And then it's up to us to decide on the amount of time. So let's say I'm going to say time unit or just time here. And let's do maybe daily averages. Okay. So the number of new vaccinations, we have to figure out how many more people got vaccinated between these 2 points in time. Okay. So what does that mean for new vaccinations? I'm not interested in the number of total people vaccinated by March 14th. I'm wondering how many more people got vaccinated between December 14th and March 14th. So that means I have to take in how many people have their vaccines on March 14th minus how many people had their vaccines on December 14th, because again, I'm only interested in the new cases, and divide by the actual total amount of time. So if we're going to do for the daily number, then in this first 3-month period, we have approximately 90 days. Let's discount the fact that some of the months were short and some were longer. We're going to stick to 90 just so that when we do the next 3 months, which is going to be the next part of our question, we have the same time period. Now, I don't actually have numbers on this graph, but I do have the graph, the same graph, but in interactive in the browser. So let's take a look. On December 14th, there were 5 people that got the 1 dose. And on March 14th, on this graph, I am going to move it until I get to March 14th. This is harder with this iPencil than it looks. There were 2,463,087 people. So let's record these 2 numbers. So what I have here are 5 people. And what I have here are 2,463,087. So now, again, I'm going to take this number, subtract the 5 people that got vaccinated on December 15th, so that I actually have the number of new vaccinations. And then I am going to divide everything by 90 as the number of days that surpassed. I'm going to round to the nearest human. And so overall, it's going to be 27,367. Now let's think about units. The actual formula gives me the units directly. The number of vaccinations per time, which we're deciding was in days. So this is vaccinations per day. Per day. Excellent. So this is how many vaccinations occurred per day in Canada between December and March of 2020. Let's do the exact same thing, but use the next period of the next 3 months to see how that number will compare. So for my next number, I'm looking between March 14th, for which I already have the number. So let me mark this again. It's 24,63,087. And then I'm going to look up the number that corresponds to June 14th, so somewhere here on the graph. I'm not going to bother going into the interactive graph. I already have the number written down here. It's 24,705,348 people. Okay, so my average going between March to June is actually the number of new vaccinations. So the new vaccinations that occurred between this point and this point. I don't care about the old vaccinations of the people that were already vaccinated by the March starting point for me now. I only care about how many new ones were acquired in between these two timestamps. So I'm taking all the vaccinations that I know have been administered by June, and I'm going to subtract out the number of vaccinations that have already been there in March. So minus 2,463,087. And I'm going to once again divide by the time period that I'm interested in. Since I'm going to keep it in days, I'm going to divide by 90 again. So again, rounding up or rounding to the nearest human, not up, just rounding, I end up with 247,136. And once again, the units are what on top was the vaccinations and what was on the bottom was the days. So this is vaccinations per day. And then I'm going to do one more point. I'm going to think of the next 3-month period. So June to September. So September 14th, let's say somewhere over here. And I know that this number corresponds to 28,486 and 247. So finally, my average number of vaccinations between June to September, I am going to take the September number and take away from it the number of vaccinations that have already occurred prior to my June data point. So 28,486,247, a lot of actual number punching. I really hope I didn't punch any of these wrong into my calculator. So make sure you do check my my actual average calculations, because these numbers might very well be wrong due to the fact that I did not type in properly into my calculator. But what I have here is 42,009. And once again, my units are exactly the same, vaccinations per day. So let's think about what that actually means overall on my graph. When I was computing these averages, what I'm taking is the difference between these 2 points vertically in terms of vaccinations. These are the numbers on the graph. And I'm dividing them by 90, which means that I'm dividing them by the distance horizontally between the two, which is 90 days here. So what I'm really doing in all of these calculations are I'm taking these 2 points and I'm computing the rise over run that led me to go from the earlier point to the later one. The rise over run, of course, always corresponds to the slope of the line between the 2 points. So what that really means is that my numbers computed so far actually represent slopes that connect each of these points. So my previous slide, I have calculated that the slope of this first line was 27,367. The slope of the second linear segment is this number, so 247,136, and the slope of this last line segment is 42,009. And now I can look at these numbers and understand a little bit better what that means in terms of the actual rate of vaccinations as they kept going in time. I start off with a fairly shallow slope, and then the vaccination rates pick up greatly. This number is almost 10 times more than the first one, so the slope is much steeper than the first one. And then vaccines again level off, but not actually to the same amount as in the first 3 months. So the key point here is that the average always represents the actual slope of what we call a secant line, just a line that connects the 2 points. Now, we were taking 3-month periods, and this is, of course, not ideal because 90 days is a long time span. In terms of COVID, generally, 90 days, a lot of things can change. So you can notice, of course, that this line, if I zoom in, even with my rough sketch, this line isn't really perfectly matching the function that is itself not linear. This line only tells me the information between the two endpoints. If I wanted to consider smaller time periods, so instead of 3 months, I can consider monthly, I can actually then connect the points between the 30 days, and I can already see that my linear segments will match the shape of my curve much better. Okay, and that's going to be the case any single time you talk about the average. The average will never tell you exactly what is happening. It will just tell you what's happening at the endpoints, but it might mislead you in terms of the information that happened in between. For example, if this graph looked crazy like this, the average will still be the same because all I can see are the actual information on the endpoints and not what happened in the middle. Okay, the average is only as good as how long you've allowed between your two timestamps to go. However, here, the information seems pretty clear. Steeper and steeper incline in the first 3 months, and then the plateau towards the end. If we are going to think about when is the steepest rate, so when were the most daily vaccinations being administered, thinking in terms of these lines as approximating our graph, I can see that it's probably somewhere, around here, right? So somewhere around June is where I can see that if I pick 2 points on the graph, I will see an even steeper slope. And in fact, we can go back to our interactive graph here, and instead of total, pick new vaccinations. And we see that indeed, now this is actually a 7-day average, so still not daily cases, but better than 3-month average that we have computed. I can see that it is in fact somewhere in June, mid to late June, that the number of vaccinations was really picking up. And this is, again, consistent with when looking at my graph, seeing where the steepest increase on this graph actually occurred. So averages, a good first starting point, but we will have to refine our concept of that in order to represent the variability that might happen in the graph between the points that you've considered. Another interesting example of average of a function to consider is when it comes to average velocity. One of the earliest examples of experiments is a famous example by Galileo Galilei, who was an Italian physicist who traveled to the, as you can see, town of Pisa in order to drop different weighted objects from the top of the tower. The tower, of course, is leaning, and therefore it's actually quite easy to drop objects off of a fairly large height without having to launch them from the distance. So what Galileo wanted to find out is, does it matter how heavy the object is when it comes to how fast it hits the ground? So he brought with him a number of different balls. Some were the same size but different weight, and some were different sized. And he dropped them all from the top of the tower. What he noticed is the balls that were the same size, it didn't matter how heavy they were, they actually hit the ground at the exact same time. This opened up a whole new area of study and opened up a lot of sort of eyes and changed a lot of minds about how gravity works. And in particular, for example, on one of the first travels to the moon on the Apollo 11, I believe, they brought with them a feather and a hammer to drop on the moon to sort of in respect in some sense to Galileo's original experiment here, to show that on the moon, when there's no air resistance, the objects will fall to the ground at the same time. The weight doesn't matter on Earth, and it doesn't matter on the moon. On Earth, we have air resistance, so the feather, which has a much higher surface area than a hammer, will fall on the moon will hit the moon from the same height at the exact same time. I encourage you to look it up on YouTube. I will put the link in the description of this video. It is a real fun video to watch about what happens with the lack of air resistance, but with the presence of the gravity. Now, we have formulas that describe how objects behave with respect to gravity, and we will derive them later in the course. For now, we're just going to see how we can analyze it within the context of velocity and the concept of averages. So let's say we are going to throw a watermelon off the Tower of Pisa. I figure if you're going to throw anything, it might as well be a watermelon. The height of watermelon from the ground t seconds after the fall is modeled by this function. So this general shape of a function is the one we're going to model later on in the course with just the bare understanding of what gravity is. This question asks to estimate watermelon's velocity in 3 seconds. So in general, you might remember from physics or simply by thinking about units, velocity is measured, let's say, in kilometers per hour, kilometers being the measure of distance and hour being the measure of time. Velocity in general is distance over time. So with this in mind, how can we utilize what our function here represents? Let's maybe draw a little picture to better understand what this is referring to. So this is my Leaning Tower of Pisa right here, and I'm going to throw an object from the top of it. It's important to know where the ground is. So I'm going to throw an object from the top of the tower. It travels towards the earth. That is how gravity works. And what this function describes is the height of watermelon t seconds after the fall. So let's see if it matches our intuition. What if I calculate h of 0? So if I plug in 0 for t here, that means that this is the height of watermelon 0 seconds after the fall. I plug 0 in for t, this entire term is going to be 0, so my answer is going to be 55. 55, and the measurement here is in meters. Notice that the tower itself is 55 meters high, so that makes sense. 0 seconds after the fall, the watermelon is still at the top of the tower, which is 55 meters high, so h of 0 is in fact 55. Great. Let's compute something like h of 1. So where is the watermelon 1 second after the fall starts happening? Well, one thing is to establish our expectation of what it's going to be. The watermelon starts falling. So in 1 second, it's not going to be as high as 55 meters. It's going to be somewhere on its way down towards the earth. So the number we get here should be certainly less than 55. Okay, let's plug 1 in for t here. We're going to get 55 minus 4.9 times 1 squared. And if we compute, this is going to come out to be 50.1 meters. So that means that in 1 second, the watermelon is up here at the height of 50.1 meters. Where is the watermelon going to be in 3 seconds? Once again, following the same logic, I'm going to plug 3 in for t here to find out that in 3 seconds, it's going to be at about 10.9 meters. Okay, so in 3 seconds, which is where I'm interested in the watermelon's velocity, as it's falling, let's say it's about here, at the height of 10.9 meters. Now the problem, of course, is I know how high it is in 3 seconds, but I don't know what its velocity is in 3 seconds. And the only thing that I can compute here with is the function of height. So let's see. The velocity is distance over time. So that means that I can compute the velocity as long as I can compute the distance and the time between the two different points. So instead of computing something in 3 seconds, which is just 1 point, I am going to actually take an average between the 2 points around 3 seconds. So let's see how that is going to go. If I compute the average velocity between, let's say, 2.9 and 3.1 seconds. So the average is going to be the total distance traveled between those time points divided by the actual amount of time that came in between. Or alternatively, we can say it's the change in distance divided by the change in time between the 2 points I'm interested in. Both of these I can compute because I actually have the formula for the distance, so I can compute how high the ball was at 2.9 seconds and how high it was at 3.1 seconds. And then, of course, I can compute the change of time because, well, this is just 0.2 seconds between those two time points that I ended up picking, right? So the height at 3.1 seconds minus the height at 2.9 seconds divided by the amount of time that came in between. Now, this is fairly straightforward. I simply plug in 3.1 in for t to compute the height. I plug in 2.9 in for t to compute the height in 2.9 seconds. I calculate their difference. And on the bottom, I already have two numbers. I can plug everything in, and I'm going to see that my overall number, it's going to be minus 29.4. And what are my units? The change in distance, the distance was measured in meters. So meters divided by the change in time, and the time was measured in seconds. So meters per second. Why is it negative? Well, notice that the ball is falling towards the ground, whereas the height is measured against it, right? So the height of the ball is decreasing, and therefore the velocity actually has a sign. It's going to be negative. Now, one question remains here is, why did I pick these 2 points? I wanted around 3 seconds, but what 2.9 and 3.1? What if I picked 2.95 and 3.1? Would that be better? What if I picked 2.999 and 3.001? Would that be better? This is closer to 3 seconds. And in fact, of course, the closer you are to the particular point, the better this average is going to represent what happens actually in 3 seconds. But the big issue is that computing the average always involves using two numbers instead of using just the one, which is the point where you're actually interested in of the situation, right? So it's kind of like your number 3 lives here, and you have to pick 2 points to compute the average between around 3. The closer you are to 3, the better. And we're actually going to develop analytical methods to be as close to 3 as possible, infinitely close to 3, while still computing in between the 2 different points. Now, an important thing to notice here is in order to compute the average velocity, we actually utilized the distance function. So the average velocity really is how fast the distance of the falling ball is actually changing. Velocity is really the rate of change of the distance, in this case, the height. Now, we're going to take this idea of the change in one variable divided by the change in the other variable and generalize it to average rate of change of a function. So let's think back to what we have in a very general case. So let's say I have 2 points, A and B, and I have a function values, f of a, so the y-coordinate for the value at A, and the y-coordinate for the value at B, okay? So these correspond to the y-coordinates of these points. The average computes the slope of the function in between, right? We discovered that in the first COVID example, is that when I just take the average between the 2 points, I essentially compute rise over run, which means that I am computing the slope of this line between the 2 points. Now, this is a representation of how fast my function is growing on average. This is the average rate of its change. However, my function can look drastically different. My function could look like this, or my function could very well look like this on the way. Both of these functions will produce the exact same average. So that is one downfall of the average. But the upside of it is that it's fairly easy to compute. So let's get back to the analytic or formulaic expression for the average. What we're interested in is the difference in the y, so the rise, divided by the difference in the x values, so the run. So the change in y divided by the change in x. Sometimes you also see this written as y2 minus y1 over x2 minus x1. So this a and b notation might not necessarily be the one that you're most familiar with. Sometimes, instead of saying the change in, the notation is introduced with delta. Delta means the difference between the two y values. So delta x divided by delta y. And of course, this all equals to the same rise over run idea that we've discussed earlier. The average rate of change, let's write this down because this is really important. The average rate of change is simply a slope of the secant line between the 2 points. Two things to notice here. First of all, we need 2 points to compute the average, so that's one issue. The other issue is the average still only gives you a snapshot of what happens from A to B. It doesn't actually tell you what the function between them looks like, and the same average could be produced by two very different looking functions. Let's take a look at another interesting example. The fastest human on Earth. The data in this table below is from Usain Bolt's first world record sprint. So the data is given to us in terms of the 10-meter split in distances, and the time that's being recorded corresponds to when Usain Bolt was at that particular distance. So we can see that he ran 100 meters in 9.69 seconds, but he was, for example, at 30 meters in 3.78 seconds. So there's two questions. The first one asks, what was Bolt's average speed over the entire race? And then the second one asks for something a little bit more interesting. What was his fastest 10-second interval? So we might actually want to know what the runner's race looked like. Was he fastest at the beginning, or was he speeding up the whole way through and actually was running as fast as he possibly could as he was finishing up? So let's start with the first one. What is the average speed over the whole race? So we already have seen that the average is change in distance. So whatever distance was covered over the change in time. So how long did it take to actually cover this distance? Now, for the entire race, we of course know that he covered 100 meters total, and he did so, according to the table, in 9.69 seconds. So meters, seconds. So if we turn this into a number, this turns out to be 10.32, and we can already see that the units are meters per second. Notice that I've simply gotten my units from the same exact table. In order for us to better understand what this number is, it might be easier to transform it into kilometers an hour because we're used to those numbers, and we will see that this corresponds to approximately 37 kilometers per hour. He was running faster than cars can be driving in the school zone. Isn't that crazy? Now, the next natural question to ask is, when was he the fastest? So here we're asked to compute the average over every 10-second interval and essentially compare. So over the first 10-second interval, he has run 10 meters in 1.85 seconds. But how long did it take him to run the second 10 meters? So the distance that was covered is 10, and the time that it took to cover it is the time span between 1.85 and 2.87. Okay, so let's say for the second 10-second interval, what we have is the change in distance is 10 meters between 20 and 10, and the change in time is how much time has surpassed between the two different time points. And if we compute that, we will see that this is 9.8 meters per second. Now, this is, of course, just the second 10-second interval. What about the first? What about the third, fourth, fifth, and so on? There's a lot of 10-second intervals to fill in here. You can do this with your calculator, or we can pull up a spreadsheet and actually calculate it using a spreadsheet. Let's see how this would work. So what I have copied over here is the exact same table as on my slide. And what I'm going to do is actually enter in the formula here. So I'm going to say equals, and then in the formula, I'm not going to put in the numbers. I'm going to put in the corresponding cells. So what I'm going to need to do for this cell here, I'm going to compute the average for the first 10-second interval. So that means I have to have this cell minus the previous cell to show the change in distance, divided by this cell minus this cell on top to show the change in time. Now there's several options. In Excel, you can grab the bottom right corner of the formula you've just entered and extend it out, and it will actually copy the formula, adjusting for the placement of the cell for you. I'm working on an iPad and Google Sheets. That's not quite going to work, but what I can do is copy the formula in that cell and then paste it in the next cell. If I click on it again, at the bottom of the screen, or actually if I double click, there we go, we see that the formula has adjusted to be for the two cells in the proper position. The formula has moved along with the placement of the cell that I'm moving into. So going this way, again, on the iPad, it takes a little bit longer to fill out as opposed to just dragging and filling it in. Bear with me here, and we will see that what is actually happening is, look, he is accelerating in the beginning. He's running faster at the beginning, and then he kind of plateaus at this particular speed for quite some time. In fact, the 2 decimal places that are recorded in the table are just enough to show that he has plateaued at this speed before the last little bit where he begins to slow down. So right at the end of the race, he begins to slow down again towards the finish line. His peak happened to be in between, somewhere in between 60 and 90 seconds in terms of his speed. Instead of doing things by hand, do make sure that you actually utilize the technology that you have at your disposal. Now, once we have this kind of data, we can actually graph it. Note that this graph is given in terms of distance versus both velocity and acceleration. So this is a bit of an abuse of notation because these things have 2 different types of units. They just happen to be reasonable enough in terms of the scale that they're on, and so we have actually graphed them on the same graph. The blue one corresponds to average velocity, the red one corresponds to the average acceleration. So now let's see what questions are being asked here. What was Bolt's highest speed and when did it occur? So the velocity or speed is given to us by the blue graph. So it's asked when did that happen and what was it? So this is literally asking for the highest point on the graph here, which I would say is about there. So at 75 meters is where it happened, 75 meters. So our point in time is actually a point in distance. And the velocity itself was, we can see from the rough graph, approximately, let's say 12 meters per second, which is consistent with the previous calculations on the spreadsheet. The other interesting thing to note here, because we have 2 graphs, is to see what that point corresponds to on the acceleration graph. So we see here that on the acceleration graph, acceleration was positive before, above 0, and then it becomes negative after. So he's actually running faster and faster and faster here. The acceleration is positive, and then he begins to slow down. The acceleration becomes negative. So surely this is the highest point because he accelerates towards it and then starts decelerating afterwards. How much time did it take Bolt to run 25 meters? Exactly. So 25 meters. Let's think back to our table on the previous slide. We know that it took him 2.87 seconds to run 20 meters, and we know that it took him 3.78 seconds to run 30 meters. But we don't know how much it took to run 25 meters. Now, we can justify the fact that 25 is halfway between 20 and 30, so probably a good estimation of his time is halfway between 2.87 and 3.87. So we can record that and then discuss how that's not actually exactly what's going to happen. So halfway between 20 and 30 meters. So time-wise, we can assume that it's halfway between 3.78 and 2.87. So we calculate the half point, and then we'll actually have to add that half point to 2.87. Now, it's not going to be quite right, and that is because we can see here that he actually keeps accelerating, right? So at the time of 25 meters, or at the point of 25 meters, he's still accelerating. So that means that he will run the first 5 meters between 20 and 25 slower than he will run the second 5 meters between 25 and 30. So this is nothing else than an approximation, and of course, it's not going to be an exact number. For part 3, how much time did it take Bolt to run 28 meters? We can apply a similar logic and figure out the fraction of the actual 10 meters that 28 is in between 20 and 30 and apply a similar formula. But again, it's going to be nothing other than an approximation. What was Bolt's speed at 25 meters? Well, the nice thing about having both the table and the graph is that the graph actually does give us the speed, the velocity. So we can take a look at 25 meters, what the velocity was, and we can see that it's going to be approximately, let's say, 11 meters per second. Now, it's not exactly that number for 2 reasons. First of all, our graph, as you can see, is jagged, which means that it's based on averages in the first place. So I took these 2 points, and much like in the COVID graph, for every interval, I simply drew the line between the beginning and the endpoint of that interval, which is why the graph isn't nice and smooth, but rather is a little bit jagged all over the place. So this point might not be exactly there. It might be a little higher or a little bit lower. This is where it is on average. And secondly, no information that you read directly off a graph will ever be perfectly exact, especially when you're producing the graph from the table of values. The graph is nothing but a visual representation and, by extension, an approximation of the actual data you're using. Having said that, the actual ability to visualize the things does help us justify a variety of concepts, right? So for example, this graph made it very clear what the connection between the velocity and the acceleration actually is. The velocity was increasing all the way up while the acceleration stayed positive. Velocity started decrease, the acceleration became negative. And there's a couple of other things about this graph that we won't be able to simply immediately catch from the table. A picture can in fact be worth 1,000 words, but you have to be careful that the picture is oftentimes just an approximation of the reality. Let's take a look at another example that is purely numerical. So here we have a table of values, much like in the Usain Bolt's case, but we're not even going to have any types of graphs. Whatever graphs have to be produced, we will have to produce them ourselves. I encourage you to pause the video and try to actually work through this example yourself before you come back and we go through this together. So what I have is a cardiac monitor that measures the heart rate of a patient after a certain number of minutes. So what I have on top is the number of minutes, and what I have on the bottom is the number of heartbeats that have been recorded up until this number of minutes. So as you can see, the number of heartbeats keeps increasing and the time keeps increasing as well. So for example, here in 42 minutes, we're going to have 2,343 heartbeats. But generally, what we want to know is not the total number of heartbeats, but rather how fast the heart is beating at any particular point of time. For example, over the first 40 minutes or between some two different time points to see how regular it is. So first of all, over 40 minutes. The average over 40 minutes means the average rate between minute 0 and minute 40. Right? Over 40 minutes. So what do we have? We need a change in the heartbeats divided by the change in time. So how many total heartbeats were there by minute 40? There were 2,221. And how many minutes have passed? 40 minutes. And so if you move that, or if you put that into your calculator, you will get 55.5. And the units are, well, these were beats and these were minutes. So what we have is beats per minute. Now, next up is the average heart rate between 38 and 42. We can actually take the exact same formula and the exact same logic and put this here, except for we're going to have to be a little bit careful about the fact that my beginning point is no longer at 0. So I have to adjust for that slightly, right? Average rate between 38 and 42. So I need to know how many heartbeats occurred between these 2 points in time. So I can take the total of the heartbeats at 42 and subtract how many heartbeats were there before 38 minutes. 2343 minus 2107, and that will tell me how many new heartbeats have happened between these two endpoints. And we're going to divide by the change of time. So 42 minutes minus 38. If we calculate that as a number, it's going to come out to be 61 beats per minute. Now, next up, we're asked to estimate the patient's heart rate over 41 minutes. Now, 41 minutes isn't something that we have in the table. 41 minutes is somewhere between 40 and 42. In fact, it's exactly halfway between 40 and 42. So if we can sort of create a table entry here with the number of heartbeats, then once we do that, we can use the exact same logic as in part 1 to figure out the average over the 41 minutes. Now, what is the number that's going to go in here? So let me actually pretend that I have this table here. So 2221. What I would like to have is 41 and some number, and then 42, and I have 2343. Now, same logic as in the Usain Bolt's example. Because 41 is halfway between 40 and 42, I'm assuming, or it's a reasonable assumption, that the number of heartbeats is going to be exactly halfway between the two numbers that are here. And if I calculate that, that will turn out to be, I'm going to skip those calculations, 2282. Once I have this number, you know what, I'm going to write down what this actually represents. This represents 2221 plus 61, which is the number. So 61 can be obtained by taking these two numbers and adding them and dividing them by 2. And then I'm going to add that halfway difference to the first number here. Now, once I have that, the average I compute as in the first example above. So it's going to be the average over 41 minutes. So now I have 2282 as the total number of heartbeats in 41 minutes. And overall, this will give me 55.6 beats per minute. Now, the nice thing about this is we can think about what this actually means on the graph. And this will likely give us another sense of how averages work. So let's think about this graphically. Remember that averages are just the slopes of secant lines connecting the 2 points. So if I draw myself a graph, again, my scale is going to be just there for making sense of the question, but not exactly necessarily proper. What I'm interested in is what happens between 40 and 42 minutes. So I know that at 40 minutes, I have 2,221 heartbeats. So this is time, this is heartbeats. And so I have a point here. And at 42 minutes, I am at the point of 2343 heartbeats. So this point right here. The average will correspond to the slope of the line containing the 2 points. So what I can do is I can find the slope of this line, and that's fairly straightforward, right? So let's write this down though, because this is a very important observation. Average rate is the slope of secant line. Now, the way that we compute the slope of a secant line is rise over run. So how much have I risen to go from this point to this point? I have risen this amount. So 2343 minus 2221 divided by the run. And how much have I ran between here and here? Well, 2, or really if we want to do the arithmetic, 42 minus 40. So the slope will come out to be 61. Now, I can actually construct an equation of this line. So digging back into our pre-calculus roots, and if you need a refresher on that, please refer to the pre-calculus refresher package. The equation of a line that will be convenient here is the slope-intercept form. In fact, for most applications in calculus, slope-intercept form is the easiest form of the line equation to use. So what I have here is I have my x and y that are variables within the equation of the line. I have my m, which is a slope, and I have x1 and y1, which are coordinates of some point on my line. So what I have here is I already know what the slope is because I've just computed it. So this m is 61. And for the coordinates of a point, I can actually take either one of the 2 points that are present. It really doesn't matter which one. So let's say I take the 40 and 2221 as the point. You could also very well use the other point. The result will not matter. Once I plug this in, I can actually expand out my equation and compute things within it. And in particular, what I can compute on it, so this is the equation of this line that goes through these 2 points. In particular, what I can actually compute is the coordinate of the point that corresponds to 41. Okay, how do we do that? Well, if I'm interested in what happens at x equals 41 that follows the pattern of this line, I can simply plug in x equals 41. And what are we going to get? I'm going to have y minus 2221 is equal to 61 times 41 minus 40. Everything is a number except for y. If I solve for y, I am going to get 2282, which of course is the same number as I've obtained on the previous slide. Now, the nice thing about this method is that it allows you to not only compute something halfway through between the 2 points, but really any number between these 2 points. So if I, for example, wanted to compute the number of heartbeats at minute 40 and a half, I don't have to figure out sort of what fraction of this line 40 and a half belongs to. It's not exactly halfway through. It's neither here nor there. All I have to do is plug in 40 and a half into this function, well, rather this function, this line here, and I will get my answer. I don't have to play this balancing game of being halfway through and worrying that I'm not at exactly the right spot. Constructing an equation of a line by computing the slope and plugging in the point will then allow you to calculate with any single point on that line. So once again, a quick recap of what the average rate of change of a function is. It's important to remember here that we're not just computing an average of something. We're computing a rate of change. How fast is something changing? So how fast was Usain Bolt running? How fast was a watermelon dropping? And so on and so forth. So once again, the average rate of change is the slope of the secant line between the 2 points on the graph. The function might look drastically different from its average rate of change, so it's not always the best description, but it's the best one we have on hand right now.